Stoichiometry practice. When posed the question, where does most of the mass that makes up a tree come from? Most people have to think for a minute. Where does most of the mass that makes up a tree come from? But if given the information that roughly 60% of the mass of a tree comes from cellulose, you can think a little bit harder and understand that cellulose is a polymer, which is a very large molecule composed of repeating units made from thousands of glucose monomers per cellulose molecule. Okay, so where does most of the mass of the tree come from? Well, most of the mass of the tree comes from cellulose. Cellulose is made from glucose. But how does a tree make glucose? You probably remember from elementary school or maybe middle school that plants make their own energy through photosynthesis by fixing carbon dioxide. That energy is glucose. The glucose is also packaged together in cellulose molecules to make the structure of the tree as well. So the same process, photosynthesis, will fix the carbon dioxide from the air, and the plant will either use the glucose as an energy source or as a structural source. So in class we asked the question, how many pounds of carbon dioxide does it take to make a 300-pound tree? Knowing that 60% of the mass of the tree comes from cellulose, and the cellulose is made of glucose, and glucose is made from carbon dioxide in photosynthesis, we can answer this question. How many pounds of carbon dioxide does it take to make a 300-pound tree? Okay, so let's take a minute and work this problem out. First of all, we need to remember that the tree is made, the 300-pound tree, 60% of the mass is from the cellulose. Okay, so if it's a 300-pound tree, then it's going to be 60% of 300 pounds is the cellulose. So really 180 pounds of the tree is made of cellulose. Okay, so then the question should really be, how many pounds of carbon dioxide does it take to make 180 pounds of the tree, since that's the part of the tree coming from the cellulose. All right, so in order to answer a quantitative question like this about a chemical change, because really it's a chemical change from carbon dioxide to the tree, in particular the cellulose in the tree, so it's a chemical change. So in order to quantitatively describe that chemical change, we're going to need to use a chemical reaction. And the chemical reaction we're going to use to answer this question is the famous photosynthesis reaction. Carbon dioxide reacts with water to form glucose and oxygen in the presence of light and the proper enzymes within the plant. So first of all, anytime we're going to describe a chemical change to answer a quantitative question about that chemical change, we have to make sure we're talking about a balanced chemical equation. And so in this case, right away, it's obvious that it's not balanced. There's 6 carbons, so we need to have 6 carbon dioxides. There's 12 hydrogens, so we need to have 12 hydrogen. And then we've got lots of oxygen over here and 6 here, and so we need to add a 6 here. So the first thing we want to do is make sure we're dealing with a balanced chemical equation, which we are. There's coefficient 1 is assumed in front of the glucose. And so it's 6 moles of carbon dioxide plus 6 moles of water. In the presence of light and the proper photosynthetic enzymes, the plant will produce glucose 1 mole and 6 moles of oxygen. So now we have all the tools we need to answer this question. How are we going to answer the question? Well, what we want to do in this situation when we're trying to get some quantitative information out of a chemical change is try to approach it systematically and ask yourself, in this case, what is the given information and what is the wanted information? In this case, the given is that we're making 180 pounds of glucose. Okay, so given that we've just made 180 pounds of glucose, which is making up the cellulose, which is 60% of the mass of the 300-pound tree, we have 180 pounds of glucose given. And what's wanted is how many pounds of carbon dioxide does it take to make that much glucose. Okay, so now we have a problem that we can solve, and we have all the tools that we need to solve it. At this point, it simply becomes a dimensional analysis problem. And that is because across the chemical change, we have mole-mole ratios, and within the molecular substances, we have gram to mole ratios. All right, so the first thing you want to do, since I said it's a dimensional analysis problem, is you want to identify what is the conversion path to solving this problem. The conversion path is you start with what's given and you end up with what's wanted. What's given is pounds of glucose, okay? And in the end, we're going to end up with pounds of carbon dioxide. But how do we convert from pounds of one thing to pounds of another across a chemical change? The ratios, the relationships in the chemical change are number ratios, molar ratios. So we have to get from a mass unit to a number unit. And we're in pounds, which is an English unit. So the first thing you always want to do is convert to grams in this situation. So we're going to convert to grams of glucose. All right, once we're in units of grams of glucose, we can convert to the number of glucose in moles by using the molar mass. So the next thing we're going to do is convert to moles of glucose. Okay, once we're in moles, we have a mole-mole ratio. For every 1 mole of glucose that's formed across this chemical change, it takes 6 moles of carbon dioxide, so we can convert to moles of carbon dioxide. And once we're in units of moles of carbon dioxide, we can convert to grams of carbon dioxide and then back to pounds of carbon dioxide. Whoops, pounds. Oh my, let's see, there we go. Pounds of carbon dioxide. All right, so then the conversion factors, the factors that we're going to need to make this conversion, we need to know what the pound to gram conversion factor is, and it's 454 grams equals 1 pound. We need to know the conversion factor here from grams of glucose to moles of glucose. For that, you'll need to use the molar mass of glucose, which you can calculate by adding up 6 moles of carbon plus 12 of oxygen plus 12 of hydrogen, 6 of oxygen. That molar mass there is 180 grams per mole for glucose. To moles of glucose, okay, then to moles of carbon dioxide, you're going to use your molar ratio from your balanced chemical equation, which is 1 mole of glucose, C6H12O6 equals 6 moles of carbon dioxide, and then back to grams of carbon dioxide. That's going to need the molar mass of carbon dioxide, which is from the periodic table 44 grams carbon dioxide per mole. I'm almost out of space here. And then back using our English metric conversion. Let's write it all out where we can see it now. Okay, here we go. We're ready to work it. We have all of our conversion factors. So we're going to start with what's given, 180 pounds of glucose. All right. To keep our multiplication and division straight, I'm going to use a grid. So we're going to multiply by the first conversion factor, which we said was, we're going to need to get into units of grams. So 454 grams of glucose is the same as 1 pound of glucose, C6H12O6. Okay. And now we're in units of grams of glucose. The molar mass of glucose is 180 grams per 1 mole, so I'm converting 2 moles. So I'm going to put the mole unit on top, 1 mole of glucose for every 180 grams of glucose, C6H12O6. All right, and now the gram unit cancels. Now we're in unit moles. Across the chemical change, let's look at that real quick. Can we get to it? Here we go. It is 6 moles of carbon dioxide for every 1 mole of glucose produced, so it's a 6-to-1 molar ratio. We're converting to moles of carbon dioxide, so we'll put the 6 moles of carbon dioxide on top. We're canceling the moles of glucose there. Now we've used our chemical equation, balanced chemical equation, to convert from one species to another. Now we want to go back to grams of carbon dioxide, so we'll use our molar mass of carbon dioxide is 44 grams per mole carbon dioxide per 1 mole of carbon dioxide. All right, now we're in units of grams. The mole unit cancels. And then I'm out of space for the last conversion, which is 454 grams. I'm not out of space per 1 pound of CO2, 454 grams of CO2 per 1 pound of CO2. The gram unit cancels. All right, let's do the math. Well, the 454 and the 454 each cancel, so I don't have to worry about that number. Makes it easier. So it's going to be 180, and the units I'm ended up with is pounds of CO2, by the way, which is what we want. Let's see. Oh my goodness, what a mess. Okay, so 180, and then coincidentally, it's 180 grams per mole for that. So the 180 and the 180 are going to cancel, just coincidentally. And then it's 6 times 44, and that is 1 pound. So those are the only numbers we have to do. And when you multiply 6 times 44, your answer turns out to be 264 pounds of carbon dioxide. So that's how we ask that tricky question, or answer that tricky question: how many pounds of carbon dioxide does it take to make a 300-pound tree? Basic stoichiometry, understanding the assumptions you need to make, understanding the photosynthesis reaction, and simple dimensional analysis. Good to go.